Okay, so in the last video we talked about this graph right here, which is the graph of a rectangle with an area of 300. We looked at the different lengths and widths of possible rectangles with the area is 300 and plotted it out. Now here we're going to extend that investigation, and I'm going to clear some of this off. What we're going to do now is talk about this as a general function and describe the function and talk about the equation and how you might go about figuring out the equation for this function if you needed to do so. And here again, what we know is that length times width, right? That's our starting point here. Length times width equals 300. Now, when you have two variables in one equation, it might be a good idea to define one in terms of the other. And here I'm going to define W in terms of L because width is the dependent variable. It does depend on the value of the length, the way we set this graph up. It could be reversed, but this is the way we set it up. If that's true, I want the equation to tell me, okay, W is going to equal something based on what we chose as an input or an independent variable for L. So how do I do that? Well, it's much easier than it looks because here we have L times W is 300. Well, by using inverse operations then, W equals 300 divided by L. Right there I'm just saying divide both sides by L, or think of this as a fact family in a way, because if L times W is 300, then 300 divided by either variable equals the other. Now we have W in terms of L, and all that means is if you want to know W equals, plug L in, and you'll know right away. So that's essentially our function. If you think about it, we're going to treat W as Y here, the Y variable, and that usually refers to f of x, right? In other words, this is the value that's based on x, your input. In this case, L will represent your x values. We could leave it in terms of W and L, but I want to move away from that and use x and y. So now the function, right, the value of the width just equals 300, right, over L, the length. And here we kind of have this interesting looking function where it's decreasing as we go along, but the rate at which it's decreasing seems to be slowing. So what's happening here? Well, here we have this kind of interesting exponential decay type function. And what's so wonderful about it is first of all, it's not linear, but you want to start to think about where this graph is going. Will this line eventually cross the x-axis? If I extend this line up, will it eventually cross the y-axis? What's going to happen here? So here's our function to predict, right, any given value. If you want to know what the width is for any length, you plug it in, and we could try for a couple. Let's say the length is equal to 50. Well, if that's the case, then what? Well, f of x is going to equal 300 divided by 50, and that equals 6. And that makes sense, right? If the 50 is the value of x, that's your length, then 6 should be the value of the width, because 50 times 6 is your area, right? 50 times 6 is 300. So you can keep testing this out, but I'll leave that to you. I'm more interested in here, the graph, what's happening. So let me just scroll down a little bit, and we'll bring this graph down. So we need more room now, because we're going to test some extremes here. All right. And I'll move over a little bit this way. Okay, so we're trying to figure out what's going to happen if we were to extend this graph. I mean, where is this thing going? Now you just saw there, if we looked at 50 for the length, the width was all the way down at 6. The increments here are going up by 20. So here with 6, right, we were up at 50. Go up to 50 on the x-axis, and you're all the way down on the y value to 6. So if I extend that, right, here we just extend this line. You can imagine what's happening. Okay, so as we extend this line on the bottom, and you can, 7, 8, 9, 10, and so forth, 11, 12, 13, 14, 15, 16, 17, 18, 20, and then you can imagine 50 is somewhere down here. That's 20, right? And we can keep extending this line, and I'm going to try to represent that. So that's 20. Let's say that 50 is about right here, okay? A fair estimate, right? Not that great, it should be further down, but I want you to get the idea of what's happening. Now here, up on the y-axis, if we extend this, right, We'll leave it open for a moment, not say how far to go. Oops. But we definitely want to extend it up so you can see how this graph is going to behave. Alright, so now, as the x value gets really large, as your length gets larger and larger and larger, your width does get smaller and smaller and smaller. But if you think about it, what happens, here with 50, see the rate seems to be, which it's decreasing, it's still decreasing, but it's just slowing and slowing and slowing. So it's getting less and less and less, but at a slower and slower rate. Right, maybe it's like down here. Okay. So it would be at a steady rate, by the way. My drawing isn't that great. Imagine the steady, slow curve decreasing, decreasing, decreasing. But where does it go eventually? Right? What's the idea of this problem? Well, the crazy thing about it is that it will never hit 0, right? The height will never go below 0. And we could try and create a negative rectangle, which I talked about in the other one, but that wouldn't really apply here. We're trying to represent physical rectangles that we can actually build, and you can't have negative lengths. For example, though, why would that happen? Let's say that your length is equal to, I don't know, 1,000. Not that large of a number, but it helps us get the idea. Well, we just said that width, or f of x, is equal to 300 divided by 1,000 now, because that's your length. When you divide by 1,000, your decimal moves how many places to the left? Well, 3. So here it would be 0.3. So your width goes all the way down to 0.3 by the time you reach 1,000. Let's raise that a little bit. Let's have the length equal 1,000,000. Okay. Well, then you'd have the width would be what? Well, it would be 300 divided by 10 to the 6th, or 1,000,000. You divide by 1,000,000, and you move 6 places to the left, and what you get is what? Well, 0.0003. Wait, did I go too far there? Let's see. 1, 2, 3. 1, 2, 1, 2, 3 brings you right here. 1, 2, 3. That's right. So 0.0003. Very tiny, but still not 0. Let's go really extreme here. Let's say a little bit higher. 10 to the 50th is L. Well, then the width is equal to 300 over 10 to the 50th. And if you divide by 10 to the 50th, you just move your decimal 50 places to the left. Or it would be 3 times 10 to the negative 47, right? This enormously tiny number, if that's a good way of saying it, infinitesimally small. That would be your width. But the length is very large. But notice it's not crossing 0. So this idea of an asymptote, that there's this boundary at 0, that you're never going to cross it. You're going to approach it, approach it, approach it, but never, in fact, reach it. And what's marvelous about these kind of functions is the exact same thing happens in the other direction, right? We're going to increase and get higher and higher and higher, closer and closer and closer to y as x becomes smaller, but never quite cross it. You can think about what's going to happen there and why, or how come it's going to happen, no pun intended there. But if x is equal to 1, y equals 300, right? But what happens if x is a half or something? In other words, we have our length here. Oops. We have our lengths and our widths. If the length is equal to 1, the width must equal 300 because the area is 300. If the length is a half, oops, the width is now 600, doubled. If the length, let's say, is a tenth, well, we now multiply 1/10 by something, right, to get 300, and that's now 3,000. And you can see how this is growing extremely fast too, in the exact same way as the y value is decreasing, as length was increasing. So anyway, there's this also an asymptote here on the y-axis. The idea of the asymptote, again, don't write that word down, is just that, yes, you can approach, right, this boundary, but never quite reach it. It's very closely to a limit. But that's for another video. We'll talk about the differences and relationship between the ideas of asymptote and limit. All right, hope this helped.